Alright, so we're gonna be doing the second part of this video, which is for doing flow simulation of this propeller. This propeller need to turn counterclockwise because the knot here will be turning clockwise, so that's how this will go. But if you're gonna do flow simulation on something that is spinning like this propeller, then we need to do a little bit extra work, and that is to create a solid that enclose the propeller. And let's start by using this face here. We're gonna create a sketch there, and so let's move here on that sketch, and now let's get a circle big enough that it can, you see, that include the borders of the propeller. That will do, a few millimeters. And just to give you an idea what that size will be, I can say 316. Make it a little bit larger. Let's see, 320. There we go. 320 is good enough. Now we're gonna extrude that, and here's the story. You see, we are in the top of the propeller, so we're gonna extrude that. We're gonna go features, extrude. Now here's the story. We're gonna remove, you need to remove the merge, because that body is very important when we do flow simulation, but it's not really, cannot be attached to the propeller itself. So basically what we're gonna do is we're gonna do here blind, and let's say that we go up 10 on that one, and in direction 2 we need to go down, I would say a little bit more than 10, 12. The idea is that you don't see the propeller. The propeller needs to be covered by this body, and that will do. I put blind on both directions, so I'm done here. We accept it, and here we are. We have our solid. You cannot see the propeller at all, but now we have two bodies here, which is the important thing. The combined body, basically, let's change the name of this. Instead of calling it combined, we're going to call it the propeller. This is a propeller, but it's a counterclockwise propeller. And the body itself, this is we're going to give this a nice name, which is going to be the rotating body. And that will do. So we end up with two bodies. Now we want to see the propeller that is inside. Just let's see how just this touch here, do a right click, and then go to change transparency, touch again, and you see it. That's your propeller right there. You see, but I have two bodies. The propeller is the way it should be, and so the rotating body. Now we are ready to go to flow simulation. Touch flow simulation, go wizard, and here let's give a nice name to this. It's gonna be propeller flow simulation. Now at what RPM are we gonna study this propeller? Here's the story. You need to think about the motor that you're going to be using. I'm going to be using a 82212 13T, meaning that motor has a kV of 1000 per volt. 1000 per volt. So the battery package that I'm planning to use is 3S LiPo, meaning 11 volts. That will be approximately, without the propeller, that will be about 11,000 RPM. So that's our first study. That will require a lot of watts, probably, you know, beyond what this motor capabilities. So this motor will not be able to spin at all my blade at that high RPM. But it's just a trial, just to see how this goes. So we said, okay, next. Now here the units are going to be SI, but I like to change here the load and motion on that one. That need to be, let's say, angular velocity. I like to change this to RPM, rep per minute, and that will do. Next, internal, no, it's going to be external. And where we are here, gravity. Well, let's turn on the gravity, and that's going to be on the y component. So let's say here it's going to be minus 9.81, and on the z there's no acceleration at all, so that's going to be 0. And let's move this to the side, so here you can see where is the acceleration vector. All right, now rotation. Oh yes. Now here's a long story. What you gonna pick, averaging, sliding, or rotating? I would say at this point averaging should be okay, because this is rotating fast enough that it's gonna get the averaging probably will be good. But if this rotate kind of slow, averaging tend to be kind of weird. The result doesn't look like they're good enough. So I would say at this point averaging. And with that said, I think that we are in good shape here. Next, now we're gonna go with in this case it's gonna be air. And next, now before I'm leaving here, laminar and turbulent, just leave it the way it is. You can pick later when you have more knowledge on this of what of any of these three will be. Definitely I will choose laminar and turbulent. No humidity. Next, roughness is a smooth surface. Next, now here we are. Air will be still, not moving at all in any direction. Now there's a parameter here called turbulent parameter. What's gonna be? I got intensity and length. I'm gonna pick what the system pick here, so I don't plan to change that at this point. Coordinate system. Well, the global coordinate system want to ensure that this is turning on the y axis, so I'm going to change here to y. And I think that we're done. Now take a while until this is done. The preparation for doing flow simulation. Yep, still thinking. There we go. Getting there. All right, here is the computational domain, kind of huge. I would say at this point, let's get that computational domain just a little bit. I will not choose too small until you do several runs, so you feel comfortable that is not, has a proper size. So I would say, in most cases, the first trial I always leave it the way it was set, but on this one I'm gonna set it that small, because otherwise it will take more time. But that's my first trial. Can always come back and fix that computational domain. So that's good enough. Now, fluid subdomain is only one fluid, air. Rotating region, that's important. Insert that rotating region, and now you can pick it from here. And what's gonna be? You have two solid, the propeller or the rotating. The rotating region is the rotating body. Now clearly it's telling us another information that is rotating counterclockwise. Good, that's what we want, and that's gonna be 11,000 RPM. You see, it's rotating counterclockwise. If you want that to rotate clockwise, then you can put a negative in front, and you can see that the arrow is turning the other way around. But in our case, we need to turn that way, and we have that clear, so we accept that. And now, but no boundary condition goals. Yes, we have many goals here. Most of them are insert surface goal. All the action here is basically happening on the y-axis, meaning what I need to see there, what I would like to see on surface goal is, let me put the body first, and that will be the propeller. And what I want There we go. What are the forces? In Y. That force in Y is important. I can put the three of them, but you will see that the only important is in Y. What else? I need a torque. Again, I'm gonna use the 3 torque, but the only one that is meaningful is the torque on the Y-axis. So let's see what else. I got everything, and all that is related to the propeller. That will do. 6 parameters. Coming back here, and that's where we are. And to complete the goals here, let's add one, which is the watts, which is very important. I mean, that's for the spec of the electrical motor that we're going to be using. It's not to exceed about 150 watts. So I need some way to calculate that. And that's very easy with the information that we have here so far and the RPM that we are establishing on the propeller. So with those 2 parameters, we can calculate an extra goal here, and that will be insert equation goal. So we're going to insert that. And how we're going to insert this expression, basically it's going to be the torque on the Y. That torque, let's open this a little bit more. The torque, we're going to multiply that times, and this will be times, we're going to go here, input data, and we look for rotating region, here, angular velocity, which is 11,000 RPM. Now, that angular velocity is in RPM. So we need to be careful here because the torque is in Newton meters. That's okay. The angular velocity is RPM. So we need to change RPM to rad per second. For that, we're going to multiply this by 2 times pi. Going to add the number 3.1416 or something like that. And we're going to divide then by 60. So 1 minute is 60 seconds. And with that in mind, I think that we have everything in the unit that we need. Again, torque is Newton meter. The angular velocity is in RPM. So one revolution is 2 pi, and then 2 pi, and then you have 1 minute from the angular velocity, which is rad per minute. 1 minute is 60 seconds, so that will work. That's perfect. So that's going to be watts, and that's let's see, we have watt here or something similar to watt in terms of let's see what we have here. Do we have joule per second, or do we have anything here? Actually, we don't. I don't see anything here that, because it's energy, but that's going to be joule per second. So actually, let's hit this with no unit, and that will be better. No unit. So we accept that, and the name of this will be watts. That will do. We accept the whole thing, and now we have that extra goal here, which is watts, for the calculation be done also by Solidworks. I think that we are ready here. Actually, how about the mesh? Let's check on the global mesh. It's gonna be 3 for the global mesh. That's gonna be automatic. If there's an improvement that needs to be done, it will be done by Solidworks, particularly on the propeller, and we're gonna leave that the way it is right now. And so we're gonna execute that. So create mesh, we say yes, there we go, the window pop, and will tell us a couple of things: total cell and fluid cells. Let's see where we are. finish normally. That's good. About 65,000 and 1400, and the contacting the solid and number of core from this machine A. No warning. That sounds good. So this looks good, and enough cells to get a good resolution, but not so many that will slow or bog down the computer. So less than 1,000 will be, less than 100,000 would be okay. So I guess that we are ready here. The only thing that I want to check is what we have here in solve. All satisfied, looks good. We got everything, and so I would say okay here. And anything else that I would like to take a look at, maybe here. Let's take a look to the mesh. Actually, if this is not created, this was created before. You can, like for example, step here and you can insert a new one. On this one is already there, so because I was running this before, so you can show that and see how that looks like, particularly here in the propeller, and where there's some improvement done to it. So you can see there, right there, some position. The iteration goes to 3. Maybe that needs better, although I can see, like for example here, you can see that it tried its best to accommodate for a better resolution right within the contact between the fluid and the solid. Maybe this needs better, the mesh side need to be improved, particularly here, like let's see what we are show basic mesh. You can see how big these guys are versus kind of a smaller on the blade, but it need to be smaller on the blade definitely, but that's what we are right now. So let's hide the basic mesh, and let's hide this guy as well, and we are ready to run and see what the system will do. All right, run, and new calculation, run. And let's see where we are now. Let me pop these. Let's say all of them. And we're going to take a look to the watts. If watt exceeds 150, we're in trouble. The negative sign, obviously, it means you are adding power to this. And let's see where we are. So it's 471. I'm already exceeding the 150, and this is the current value, so keep increasing. Now,
a few minutes later.
All right, so within 5 minutes, the system finished and 323 iterations, and you can see the result here, particularly the force in the Y, about 16 Newton, which if you divide that number by 10, force equal mass times acceleration, and being gravity, that means you divide this by approximately by 10, that's 1.6 kilograms of force that you're talking about. That this propeller is, pushing air to 1.6 kilogram. A little bit above. 1 kilogram is 2.2 pounds, so it's a lot of to be so tiny. But what's the bad news is that it requires about 1,000 watts. Will exceed the capacity of the motor, which is 150. So definitely this would not work. You're not gonna get that close at all into getting that amount of force, which is 1.6, approximately 1.6 kilogram. Well, The other forces, as you can see, are not appreciable. They're small in any means, and so the torquing X and the torquing Z, because obviously the propeller is spinning on the y-axis. So that's what you have here, that torque. And anything else here that I should kind of mention? Well, I can certainly, now that I have here, so let's add now a cut plot just to see the wind profile that is being generated here by the propeller. So let's see, insert, and front plane looked good, and contour, perfect, and I'm gonna leave velocity. The number here, you can increase it. It's 40 right now. Looks okay. So let's accept that. And it's gonna be velocity. You can change this to pressure you want to, but at this point I want velocity. And I never try, like always try velocity. Let's see those vertical velocity on the y-axis. Let's see how they looks like. Hard to tell. And there's some red stuff coming very high speed here, 104, and down 88 on, and so that's on the y. Go back here and let's put the total velocity, and that looks much better. At 50, you can see where the strong downward wind is happening right at to the middle of the blades, pretty much. So that look good. Double click here, always good idea, and check here. You have the global maximum is 179. Wow, that's a lot. And where I'm right now cutting is what, about 54. So see something here, if this improve a little bit better, because it's hard to tell. And so that looks definitely better. And let's look into this one more, but now that I changed the logarithm, let's change to this guy, the maximum, and let's go back again to cut plot and show plot maximum, just to see where it is actually. Let me see, let's go back here, right there, and let me double check here something, and that will do there. How about here? That's plot maximum, and that's global, and I'm pretty much on the global. Hard to tell because when you hit the global here, then let's see where we are, 179. Well, it doesn't look that bad. Can tell where you get the plot, but let's see, go back to cut plot, and it's just plot. All right, just the plot. So, and the plot, for example, you step here and you can move these, and you can animate that. Let's see, play. See how the color is changing as you are totally out, and then you come back because you're getting close to the propeller, and so that's kind of nice. there's somewhere here that there's a maximum that can get this high, but at this point I'm not sure this is possible, but it's just part of the calculation. And again, the issue here is this is way too high, so meaning that the RPM that I pick on 11,000 is way too high as well. So let's stop here and let's do a final calculation here. So let's go back here and stop the animation, and let's do a copy of this guy. We're gonna copy that, clone, but it's not gonna be called 11,000. We're gonna reduce the RPM to something more meaningful, about 5,000. And now let's go to rotating region, and here's the angular velocity. Rotating region again, and it's gonna be 5,000, and everything else looks good. I don't think we have to do anything except run now, and new calculations, so run. And with that RPM, I should be close to the 150 watts, and we'll see if I can either have to drop the RPM or increase it to get to 150 watts. I mean, again, the 150 watts is, I believe, is maximum, meaning that I should stay, below that 150 maximum watts. So we'll see. Start to calculate right now. You can see numbers, but a little bit obviously more meaningful, like 66. We'll see it drop to 11, although the average is 57. We'll see. Current value. About the torque. The torque here, this is the one that we are interested. It's yet to calculate it better. I don't see meaningful number yet here. About the force, doesn't make sense. The force yet. We need to change to. Here we go. It changed now. The current value changed to positive. Now that makes sense, but it's going back to negative. So that's part of the iteration process. What we're gonna do is step out and return later.
A few minutes later.
All right, so we are back here, and my friend Solidworks finished it. Solve is finished without any warning. Here are the values. Let's take a look. Now we are running our propeller at 5,000 RPM, and the number seems a lot better, within the capabilities of our motor, which is a A2212 13T. That's a T13. That's what it is. And the watts is below 150. That is good. But the force obviously drop to let's see, that divided by 10, that's going to be about 0.35 kilograms, a lot less than last time, but within the range of that motor. So definitely the motor can spin a little bit faster, let's say 6,000. But then as you are trying to get what is the proper RPM to run your motor at 150, it becomes sort of like an iteration process. The good thing is that I have the 11,000, where the watt was about 1,000, and now I have 5,000, which is about 101. So it is a lot closer to 5,000, the actual number, just to be at 150. So you can clone this back again and increase this to about 6,000, or you can do a regression line. So in order to get the proper number here that you will do this clone, another clone here, you can do like a small regression line in Excel where 11,000 is equal to 1,000 watt, 5,000 is about 101 watt shown here, and then what would be the value that you need to run this to be at 150. So you do a regression, and then you interpolate for that value, and that will do. Probably is we can do that in Excel just to get the next number, and or you can allow in this case Solidworks to do multiple iteration on that until it reach the proper RPM that this motor will operate, which is about probably it's about 6,000. I mean, I can do in Excel what that's gonna be. Let's see. Let's do it in Excel in 1 second. I'm not trying to be very detailed on this, but more like to give you an idea of what should be the next value that we're gonna use as soon as Excel is up and running. We're gonna clone that, and we'll see. While that's happening back there, I can clone this guy and clone, and the name of that guy will be whatever I come out from Excel. So let's go back to Excel. Let's say a new one, and here's the story. This is what you're gonna do. I'm gonna close this, yes, later, and let's pop this big so you know what I'm doing. Like, for example, what I was saying is at 11,000, let's put here the title so you understand what I'm doing. Insert. So this is gonna be RPM, and this is gonna be watts, and this is about 1,000 if I remember that right, and this was 5,000, and this was about, what was this? This was about 101. And the question is, what will be the value that we need so that let's do it like that. Let's get this plotted so you know what I'm doing. Instead of, I want to do an equation here very quickly and allow my friend here Excel to do that. So let's see where we are. Let's get this smaller. Let's see, 11,000 is about, let's see if this is right. Let's see how this is plotting. Well, it's plotting the wrong way, so I gotta fix this. Select data, edit, and basically the X, let's do on the X, it's gonna be these two, and let's do on these, on the Y, are these two. So we say okay now. Okay, and now I think that we are right. We are okay. So meaning that 11,000 is about 1,000 watt, and here 5,000 is about 100 right here. That looks good now. So let's do here regression, a trend line. It's going to be a straight line. Display equation, and obviously the value of R. So here we have our equation, and the question is, what need to be the value of X so that Y hit, in this case, the 150. That's basically what I'm looking at. So you can do that. Let's do that right here. So actually equal. So we're going to copy that. The idea is to put your equation in terms of X. So that means Y, in this case, 150 plus, get this to the other side. So that's 648.17. All that, put it on parentheses, and then divide by whatever is under X, and then you get the RPMs. So that divided by the by that number, that is 0.1498, and that's basically the RPM that you need. So you need about 5,328. This is an approximate value. So my clone, when I go back to, I might say like 5, I'm gonna use that number. So I'm gonna copy that and go back to your Solidworks, and here, instead of being 5,000 on this clone, we're gonna change the name. Instead of having all those decimals, that would be good enough. So it's 5,328. We're gonna use that, and there we go. So now you are ready to run at that new RPM, and let's do that. Actually, now that we are pretty much ready, let's run at that actual speed RPM, and let's see what happens. I don't have to change anything except going back here and ensure that you change obviously the rotating region, because it's not 5,000 now. You can paste the number that you but instead of have all those decimal places, 28 will be more than enough because that's actually the name of your clone file here. So save it, and we are ready to run a new calculation and run, and let's see what happened. So probably that's the actual speed that this motor can sustain with that propeller, which is about 12 inches in length. And let's see how this looks like. As always, we kind of wait for the few calculations just to ensure that there's no bugs or anything that might happen. And so we wait a little bit. There we go. Now what we're gonna do is bail out from here and come back about 5 minutes later when this is done. So all right, we are back. This is done, and so let's finish it. No warning, everything looks good, and we are below. Should be about 150. We are 123. Got a little bit better, but not yet on the 150. So that means that we need to go back and do a little bit more iteration. So I need to increase the RPM, and you can do that. I'm not gonna do it, but I'm gonna go back to Excel and improve that at that speed. At that 5,328 RPM, I got a negative 123. Obviously, the force drop, well, it's about from a little bit higher, about 0.4 kilograms. That's not bad. And so let's go back to Excel. In Excel, this is what we're gonna do. We're gonna insert a point here, insert, and we're gonna insert the 5320A, and that's about 123 if I remember. And we got the 3 points there, but let's see, it's not a straight line as you thought. It's getting there, but now the numbers are improving. So what I'm looking at is to fix this with the new equation that is here. And basically one quick thing that you can always do, like instead of waiting for this line to pop up, you can always ask for example, what is the equal. You can write the slope of this. Now nose-wise are these, and you put a comma, and then nose x are these, and that will give you obviously the slope here. But then you can write here the intercept again, no, not integer, it's gonna be intercept, and this is the nose y and comma, and this is the nose value of x, close parentheses, and that will be this value here. But the idea to have it here is that you can update quickly whatever you're doing, and basically your new value, actually it's called here, this value that is here needs to be updated, and that's basically what I'm saying. But you can, let's put it here, equal, you're looking for 150, then you need to add that number there. It's gonna be now positive, so that will be plus, or you can put a negative of a negative that will be added. So between those two numbers, let's close the parentheses and divide that by this number. So I'm not writing anything, that's what I'm saying. And the new number is 5411. So you just go back to your Solidworks and do a clone again, and clone, and that clone will be again at 5411, 5411, and we accept that, and we go back and change the rotating region RPM, and that's 5411, accept that, and that should be pretty much what you're looking at to get as close as possible to 150. And this can be also done automatically by Solidworks, but I'm not gonna do that. I mean, at least not at this point. I'm only telling you if I'm doing this manually how it's done. So I'm looking for that particular RPM that's gonna hit the 150 watts on this propeller, and let's run this one more and let's see what happens. So I change everything again, ensure that you change 5411, and we're ready to run this. And new calculation run. So let's go back here, and again let's ensure that this is moving right, no hiccups, and as long as it's running, so far so good. I don't see issues. The only thing is I want to be sure how close this get to the 150 eventually. Doing the iterations, and as always, let's bail out and I'll be back when this is done. It takes about 5 minutes or so. There's not many points to deal with. So alright, so I'm back here, and it's pretty much done. It's just, you know, calculation is pretty much getting there, and I'm gonna stop it because what? I'm hitting the 128. Clearly this is non-linear. That's the problem. It's non-linear at the with the RPM. So this is what we're gonna do. We're gonna stop. You can save. You can say yes, and then go back to your Excel here, as I'm showing here, and yeah, it's just updating. So let's go back to Excel, and in Excel, this is what we're gonna do. We're gonna increase this, and we're gonna add another line, and that line is the new RPM. So it's 5411, and it's 100, I believe 128, I believe it was. Let's see, go back here, 128, 129, it doesn't matter, 129. And now instead of using a straight line like showing here, which is clearly telling you that it's not a straight line, it's dropping, and let's improve this with a better line. Let's leave that for a second there, and let's step here on the point, and let's do let's see where we are here. See, format red line. Instead of being linear, let's see what we should do. We should use polynomial, and here is a better line with r equal 1. That's perfect. That means that's a great correlation between this 3 point and this last point here, far away. With the r value that good, what we should do now is use this equation to interpolate, and what should be the x value to getting the y equal basically 150. It's gonna be a little bit hard because it's a square equation, right? So you need to solve for x, and x, you will have two values, and one of them would be really off, and the second one would be the right one. So you got to solve that for that quadratic equation there. And let's do this. This is what I'm gonna do. Like, for example, instead of solving the quadratic, I'm gonna use a trick here. For example, let's copy the whole thing. Let's copy this. I'm gonna copy all that. Copy, and now let's put that here, equal. And before you leave, here is the value that you're gonna pull for that x value there. Say yes for its time being. Oops, and let's fix this. This is what we're gonna do. So let's delete all this because it's kind of confusing the way it ended up, because I would need to understand that this x squared is gonna come time this value here, and that's gonna be square time x, and that x here is gonna come also from that value here, and then you're gonna add the 155.43, and that looks good. So right now the value is 0. So here is the x, and here's the y value. Let's see where we are. X. All right. It's interesting, right? So let's put any value here. Let's put 5,000. Let's see what's the prediction. 5,000. Something ain't right here. Let's see what is not right. I got 6. Let's add 8 decimal places just to ensure that I have enough decimal places, because that's a problem. Sometimes it only show you the 1 here. If I drop this to 1 decimal place, it's gonna be looks ugly, and you cannot use this equation to do anything with it. So at that point, I can definitely use it, and this is what we're gonna do. Control copy. We're gonna put that here, and before doing anything on this x squared, basically what we're gonna do is use the value times this value here nearby, and put that to square, and change this x as well to nearby. That's going to be time this guy plus 155, and that will do. So in other words, let's see now, when x is 0, you're going to hit that value. Obviously that will not make any sense, but because it's not going to be 0, it's going to be about, let's start with 5,000. So 5,000 is 101, exactly what I got here. Now it's very non-linear, that relationship. What is happening here? Let's go like this. So so we increase to 6,000, and let's see where we are. At 6,000, we definitely will go up, and so let's use this 5411. Let's see where it hit down. 5411, 129, 129. That's perfect. So that is telling me that this square equation is doing right. Now what I need to do is, like, for example, what will be the value that for this to be exactly 150? So we need to iterate on this one, and that's easy if you are in Excel, because basically you go to data, and let me do something here for you guys. Hold it. Okay, I'm going to data, and data, go to solver, and in solver, this is what we're gonna do. We're gonna say that this vector here, I want to have a value of 150. That should be 150, and by changing what? By changing this guy. And anything else? No, I think that we are good. Non-linear, okay. Now get this, remove that in case you want negative value as well. I don't mind at this point. So let's solve, and keep solve a solution, solve a final solution. Okay, and here it is. So at this value, at 5679, I should hit the 149, 150, basically what I'm looking at. So this is the actual value that I'm looking into it, somewhere here, for hitting the 150. And following what I see on this equation, that's perfect. So I use solver to do that. I know what is the value. It's 5679. We go back, and finally I think we should be doing this right. So we're gonna clone that one, and this will be the last one, believe me. I don't want to do this. The value again here, copy that. So we go back to Solidworks and change this. It should be the final iteration on this. And the issue is 80. I can get this to 80. Let's get that to 80 here, and that will do. So this is actually the number of the RPM that I'm gonna use. So we're gonna copy that, and we're gonna change the rotating region to that value, and we accept that, and this will be the final. that should hit 150 watts, and we'll see how close we get to that. So let's run, and this is the last one. Let's see where we are here. That would be this one, and we wait. And let's see how this behaves. As always, we kind of step out and do something else. So we bail out from here, and I come back when this is done. Alright, so this is pretty much done. 147 of 148, that's perfect for me. So that gives you the idea of how can you do this manually. Basically, I did everything manually, but it can be done fully automated within Solidworks, and you just pick the ranges, like for example 11,000 that give you 1,000 watts versus 5,000 that give you 100 watts. So the number must be the right number, must lie between 11,000 and 5,000, which is eventually we hit manually the 5,680 RPM for getting about 150 watts. But again, this is done at a given resolution. You remember that was done on a global mesh here. If I show you back that, show basic mesh, actually global mesh here, that's about 3. So you need to increase that and figure it out how the improvement that you're gonna get as you reduce or increase the number of cells, right? So I'm not gonna do that in this video, not at all, but I'm just telling you how can you get meaningful data, meaningful information for this propeller that we just constructed, and we figured out what that propeller will do. Basically, if I install that propeller in a motor that is a brushless motor, which is the A2212 D13, and I need to spin it at about this RPM, and that will produce about 0.45 kilograms of force, and so that's a little bit of close to a pound or so. But that's the kind of information that you need to now confirm with an actual experiment, in where you set this propeller, you kind of do the 3D of this propeller, install it, and have a kind of a gizmo to measure the force that this propeller will push an airplane or something. Well, that's more than enough. Thank you. Have a great day. Bye.